Hello again. In this video, I'm going to introduce concavity. And I say introduce it. I used that word already when we were talking about the second derivative. But now we've reached that point in the textbook, and we'll talk about it in a little more depth. So the derivative. The regular first derivative controls whether a function is going up or going down. And that's important, right? That isn't nothing. Are our profits going up or down? Is the number of sick people in an epidemic going up or down? These are obviously things we care about, but not the only thing. Speaking of an epidemic, let's envision or let's draw a little graph. The number of days into an epidemic will be on the x-axis, and the total number of sick people will be on the y-axis. And a graph like this is often logistic. I think I've used that word before, but something like this. We start with a small number of sick people. And as the epidemic progresses, the number of sick people increases over time. And maybe initially it increases slowly because if this epidemic is spread person to person, I guess if this sickness is spread person to person, then if there are only a few sick people, there are only a few people spreading the sickness. So it increases slowly. But as more and more people get sick, more and more people are spreading the disease. So it eventually picks up speed and increases faster and faster. Now, epidemics don't go on forever. Well, this isn't, maybe I should put asterisks there, but in general, you expect sicknesses to wear themselves out in some way. Whether it's just a flu has swept through an elementary school and all of the people who basically everyone's already gotten sick. Maybe a vaccine is developed that gets it under control, but eventually the tide starts to turn, and the rate at which people are getting sick starts to decrease. And now the function is still growing, but it's growing slower and slower. And we can have a graph like this. This is a logistic curve. It's sometimes called an S-shaped curve for probably obvious reasons. It looks kind of like a stretched out S. Now, this function is always increasing. It has to always be increasing because this isn't the number of people who are currently sick. This is the total number of sick people, or rather, the total number of people who have ever gotten sick. It doesn't make sense for it to go down. So this function's always increasing from the point of view of the first derivative. The first derivative is always greater than zero, but a change happened at some point over the course of this sickness, right? Initially, the number of people getting sick was accelerating and the disease was getting worse and worse. Then at some point, the disease started to taper off and the situation started to improve. And that happened around here. And if you look at the graph before that point, and you look at the graph after that point, there's clearly a difference between these graphs. Like, I think the imagery that I used when I introduced the second derivative was to think of the graph as a physical slide. So here, kids can slide down the slide. They start at the top on the upper right, and they slide down to the bottom. Here, we've taken that slide and we've flipped it upside down. So it's still going up, but you can no longer ride on it. If you try to sit on this slide, well, it's upside down and you'd fall right to the earth. So both these graphs are increasing, but their shapes are different. In one of the cases, the slide is right side up. In the other case, the slide is upside down. And for cases where the function is decreasing, you can also draw pictures that look like this. This slide starts on the upper left and it decreases to the lower right, but it's upright. You can go down the slide. This slide starts at the upper left and goes down to the lower right, and it's upside down. If you try to sit on the slide, you'll fall right off it. So we have four graphs here. The upper two graphs, the first derivative is positive. The lower two graphs, the first derivative is negative. And how do we distinguish, say the derivative's positive, how do we distinguish between these graphs? Or if the derivative is negative, same question. There are two graphs, how do we distinguish them? Well, I've used the phrase first derivative, which we rarely only do if we're trying to distinguish from the second derivative. So maybe you can guess that the second derivative is controlling the shape of the graph as well. In the two rightmost graphs, where the slide is upside down and you can't go down it, the second derivative is negative. In the left-hand graphs, where the slide is upright and you can go down it, the second derivative is positive. When the second derivative is positive, we call the graph concave up. In addition to the slides, I often suggest that students keep track of this by thinking of a cup or a bowl. An upright bowl holds water. Upright. And you see an upright bowl is created by taking a decreasing concave up function and attaching it to an increasing concave up function. When the second derivative is negative, we call the graph concave down. And again, although the image I've given you so far is a slide, I most often think of this as a ball when I'm trying to keep these straight in my head. If a ball is upside down,